All right, so how do we get into design? As we start designing these simple connections, we're going to use those assumptions about our behavior, and we're just going to rearrange these into these stress equations to find area, right? We said earlier that normal force is equal to, stress is equal to normal force divided by area. By rearranging this, we can find area if we know what the allowable stress is. And oftentimes, this is something that's based on a material and the type of loading that we can that we're applying. So we can actually look this sort of things up in tables or material handbooks. Same thing for designing for stress, or shear stress. Here's a great example of an axial stress. This is a bearing case where we have something bearing down on top of our concrete pad. We're trying to figure out what the area needs to be at the bottom of our steel column. These base plates kind of help us distribute the load. Steel is a very strong material, but it's pretty costly. So we don't, and it's hard, you're always going to have concrete foundations. So if we're thinking about our foundation, we want to spread out that load to concrete pad. We need to figure out what size base plate we need. This would be a great place where we could figure out, based on the allowable stress of our concrete or our foundation, we could then figure out what area we need for our base plate, make sure that our column doesn't punch through the floor, which would be very, very bad. Here's an example that we might use for shear stress. A very common connection detail for construction is to drill a hole in a concrete wall and then blow out the hole and then put use epoxy to glue a rod inside of it. This is a very common anchor design. If we want to figure out how far we need to embed this thing, we need to know what is the allowable stress of shear stress for that connection between our concrete and our glue joint, basically. We can use that to find our embedment depth based on our diameter and our allowable shear stress, right? This is basically calculating pi times d times L would give us the surface area of that contact. So by rearranging this a little bit, we can figure out what that embedment depth needs to be. How do we actually analyze this? Well, first we're going to figure out what our critical sections are, right? This is a guess. And oftentimes, when we do this, we're going to be checking multiple sections, right? We are guessing, you're going to make assumptions, but you need to check at every critical section where you could see failure, right? If we miss one, that could be catastrophic. So make sure that you take the time here to check every critical section. If we're unsure, check it, right? If you're unsure if it's critical, go ahead and check all those sections, anywhere that it could fail. We want to find those internal resultant forces using those method of sections at any place we have a critical section. And then we're going to use allowable stresses and those internal forces to help us size the members or check our design, right? Designing is sizing members. Analyzing is figuring out what those stresses are, or using the stresses to figure out what our maximum load is, where it's being controlled. So either one of those cases, these are two sides of the same coin.